for this presentation, and we'll go from there. Oops. All right, so let's go here. Okay, so as I said, this guys will be the last chapter that we're going to cover in this class. Renewable energy. Anybody have done, as I said, renewable energy, guys? Solar or wind? Solar and wind. Just a quick note for all of you. You guys will be witnessing 6 panels that we will be putting right on the roof here before the graduation with an interactive inverter. So residential utility interactive photovoltaic systems. When we move into the commercial, we're talking here residential. When we move into the commercial era, I would like to challenge you guys, all of you, especially the A students. We have a few of you guys, A students, on designing a solar system on a roof of the commercial building. So that's going to be a challenge for all of us. We're going to do the complete system for the commercial building, and at the end, my challenge would be for the A students. And the one who will go to the next level is to put a solar photovoltaic system on the roof. Okay, so the NEC code book guys talk about the solar photovoltaic system in a whole article. Solar energy is not new energy. In the NEC code book guys talked about the solar since I believe 1984. There's a whole article about the NEC about solar since 1984. Article 690. If you guys go to Article 690 in your book, please. Article 690, 690, and 690 talk about solar photovoltaic systems. So this is not new. Article 690, like I said, talk about photovoltaic. It's actually since believe it or not, it's since 1984. The NEC code book has this article since 1984. Recently becomes, in the last 10 years, it becomes a big potato. It's going down a little bit right now because of the economy and the federal fund that they not a whole lot of money right now, but it's becoming a big deal. So we're going to talk about why it's becoming a big deal, the solars, even though it's actually has been in the code since 1984. Okay. So a couple of things I want you guys to do. Identify a couple of things we're going to do. What are the major components of an interactive solar photovoltaic system? The major component of an interactive solar photovoltaic system. To summarize this, Zach, everybody knows what a solar system is. You put a couple of panels on the roof and you tie them to your house and you get free power from the sun. That's really summarize the whole business. But obviously, that's a talk of my grandma and your grandma. They talk about this. But us as designers and engineers, we don't talk just, oh, throw a couple of panels, tie into your system, and you have free power, right? That's a talk of grandmas. Talk of engineers like us. What are the components? How do you put the system together? How do you design it, right? Isn't that why you guys are here? To know how to design all these systems? Okay, so we're going to talk about identify the major components in a dwelling that are related to the photovoltaic system. Electricity is all about hazard. When you have solar system on the roof, guys, there's a hazard of shock hazard as well as arc and fire hazard, right? There's an arc hazard, fire hazard, burn the building, and shock hazard. So we'll talk about this one. The NEC requirement, Article 690. We'll talk about Article 690, the NEC requirement. Oops, that's going all the way. So the NEC requirement that we'll be talking about this one for the installation of an interactive photovoltaic system. And if you guys go with me, so these are the things that we're going to do. What are they? What are the major components and what's the code requirement? Can I have thumbs up, Chad? I know it's Friday and you guys thinking of the weekend, but keep it here with your friend Chad. So really simple. What's the photovoltaic system? What are the major components? And what's the code requirement for installing a system in a house? We have another chapter, guys, next quarter about commercial. So we're going to do it for a commercial building, and I will make it, I don't want to make it a requirement, but strongly recommendation, as I said, to put a solar photovoltaic on the roof of a building that we're going to do next quarter in Revit. That will be really cool. The first time I'm going to do it. I had a student 2 years ago did something on a house, so it was a really cool project. Okay, photovoltaic, why it's popular? Why the popularity right now, even though we have been 1984? We have been in this business since 1984. Why it's popular? Increased use of electricity. Obviously, we're consuming, and when we say popular, guys, popular in the U.S. We're using more electricity. You can argue now because of the economy. Actually, it's not really true, but because of the use of electricity. The second thing is the cost. The more the electricity goes up, the more renewable energy become more attractive, right? More attractive. So use, the cost, and the single most important thing. I know Brian, my friend, is a tree hugger like me. Anybody's a tree hugger here that can admit? No rabbit huggers, tree huggers in this town. What's going on with you guys? Okay, now for the tree huggers like your friend Chad, environmental concerns. By the way, if you work right now, you used to be only the tree huggers care about the environment. Right now, every company that you work on, Michelle Cooley, Halberg, People's Electric, Parson, everybody wants to be at least seen as they're environmentally responsible. A lot of people are spending a lot of money to be seen at least that they care about Mother Nature, and they're spending a lot of money to be at least to be seen. And I believe a lot of people believe in saving the environment. So environmental concerns, fossil fuel is making holes in the ozone, and your children 50 years from now, they're telling us they might not be able to breathe, and all this, you know, the whole controversially about the ozone holes and so forth. So environmental reasons, and it's becoming economical reasons, really. If you talk to a lot of people, guys, they'll tell you green, green is green. Green is money now if you design something green. So a big deal. Foreign oil dependency. We have been talking now, talk like politicians, dependency, being independent in foreign oil. I don't want to talk about that one. Increased efficiency, and so that's my favorite. Also, the efficiency of the PD system is becoming really good. Meaning, you can have. I think the latest I looked at or I read about, you can have close to 400 watt. What is it? What did they say? 400 watt. They can make panel that make one panel that make 400 or 350 watt. One panel that make 400 watt. That's a lot of watts in one panel. So they're becoming more efficient, guys. The technology is becoming more efficient. They're making more juice out of these, panels. So when they make more juice and they can compact them together, so they make financially more reasons. Any question, guys, about these reasons? This is just the politics talk, right? This is just talking politics. Installing these systems is not complex. You know what, Jeff? You're a journeyman electrician. You know what I tell my wife? I said, you are an electrician. You can do electrical work, you're right. But you're going to burn homes and all this stuff. You're going to learn from your mistakes. And when people, I've been a trainer, guys, and an engineer, and electrician for years, 23 years right now. You know what I say about anything? Everything is doable. Everything is doable. But until you do it, Darren, it's rocket science. Until you do it, it's rocket science. Putting a solar system on a roof is doable, but if you haven't done it, if you haven't encountered the hardware that you need to mount to the roof, the wiring methods, all this stuff, it's to you is rocket science. You don't know it. Does that make sense? So it's not complex, but unless you do it, it's rocket science. Continue to be. There's significant differences compared to the typical residential wiring. Now, you guys remember the war between Edison and Tesla? Everybody remember the current war? The AC versus the DC? Now we're getting back to that system. Remember that we on Earth, as a matter of fact, not just in America, we have standardized to use AC as our distribution, our generation, almost generation distribution, and utilization power, source of power, AC, right? 120. Now, this particular system goes back to the DC, back to the DC system. Now we're talking about generating on a DC level. Can I have thumbs up, Ted? We hopefully understand that this system is different than the residential by we're generating at the DC level. Cool. So a solar photovoltaic system is, in a sense, a generator. It's not a load, right? Everybody understand? When you put a solar panel, you have just installed a generator. You're generating power. You're not installing load. Can I have thumbs up, right, Chad? Cool. You guys are cool. And we have a whole article that talks about this, and I'm going to summarize in a few seconds. And we're doing, so the difference really is you are installing a generator that generates DC, though. That generates DC. Unlike the generator that we were talking about yesterday, we were generating AC 240, 120. This one is going to generate DC up to 600 volt for residential, and higher than that for commercial. Okay, major component. The major component of a PV system, that probably will be on your test, guys. Basic major component of an interactive system. The reason why they call it interactive system, guys, because this system will not work, Andrew, my friend, this system will not work unless you're tied to the grid. If you lose the grid, what happened to, do you guys know that if you have a solar system and the grid is down and interactive, what's happened to your interactive system? It shuts down. That's a drawback of interactive system. They have a bunch of systems. I'll show you the system that they use. But interactive system works only if you have power. If you have power from the grid, they sense that there's power in the grid, they keep supplying your house with solar as long as the sun is there. The minute that they lose power, by standard, by UL standard, you have to isolate yourself from the grid so you can feed the power back to the grid. Okay, modules, the panels. Here's your panels. So it's made out of panels. Number one is the modules. Number two, you need the hardware to mount these panels. Here's the hardware that you're going to be mounting these panels on. Number three, you need a box, a combiner. You have to combine these panels in a box, right? This is called box combiner. And number four, you need to inverter. You have an inverter to invert that system, right? So here's my inverter because this is number four. So this is my number one, this is my number two, this is my number three, inverter and combiner. No, number one is the panel, number two is the hardware, number three is the combiner, inverter is number four, and then several disconnects. What they do, the smarter than Chad guys, they put a couple of disconnects, one disconnect here and one disconnect here by code, and grounding system, and then they tie it to the panel. From here, you tie it to the panel. You are looking at a solar photovoltaic system, a panel to a combiner, a box. From the combiner, you disconnect it. From the disconnect, you go to an inverter. Up here, you can have up to 600 volt DC. Right on this side, in dwellings, they go to 240/240/120. 240/120. Any question, guys, about this? These are the major components. Grounding, they also take a grounding conductor all the way to the ground and the panel, through the panel, so they ground the whole system with number 6 copper conductor. Any questions, any comments? Any questions, any comments? Everybody knows the modules. Oh, there's a nicer picture about the whole system, guys, that can get you. We'll look at it in a second. So photovoltaic modules, the modules themselves are the basic unit of reducing power. The way we produce power, guys, is by the modules, right? These are the basic, the ones that cooks. How do they manufacture the power? How do the modules do the power, guys? They have semiconductors, PV cells. This is the source of all power. They have a semiconductor PV cells. When the sun hits them, by design, they generate a tiny little voltage and current. You collect all these tiny little voltage and current, Aaron, my friend, together in a big module, and you get yourself what? At a 200 watt, a 24 volt module. So it all starts with a tiny little cell that you hits it with the sun rays hits it. You hits it, you generate voltage and current. Can I have thumbs up, Chad? We completely understand. Do you guys see any rotating things? Is there a diesel engine generator here? No diesel engine generator. And of course, these cells, they have to be put in a frame, and typically aluminum frame. Anybody knows why they use aluminum frame with these? Lightweight. Thank you. Lightweight. You're putting them on the roof. Do you really want to use steel on the roof? Okay, so let me just flash this picture, guys. This really nice picture, and talk a little bit about it. So here's a typical system. I want you guys to look at this. This is a typical system that you have. So you have here's your solar panel. Let's just start with one solar panel here. The modules. I don't know if you can see the modules. Here's my modules. One single module. So you start with one single module like this. This one is 24 volt. Let's see, 24. Cool. Now I want one genius guy to tell me, if you put two 24s in series, what do you get? like batteries. Put batteries to 24 volts. Series, in series. What do you get? How much?
48.
48. Thank you. So the system here, assuming all the voltage system of the whole deal here, assuming this, I'm just assuming here, it's 48. 48 volt. Now, can you guys see, how about the other system right next to it? 48 and another 48, right? So the way they do them, guys, is they take, here's a module, here's another module, here's a third module, and here's your plus, minus, plus, minus, plus, minus, and you go from plus to minus. See how they do them? So we went minus, plus, minus, plus, and minus, and plus. Each one of these 24, 24, 24. What do you get? 48 volt. Can you guys see that? In series, plus, minus. Very easy, very simple. Like batteries. Do you remember how you put batteries in? Exactly like you put batteries. Now, what happens if I need more voltage? Anybody genius can tell me, what if I want to go higher than 48? What do? You put more what? Cells. In what? In series. You guys got the solar photovoltaic system. You can keep ramping up these up to winning 600 volt. Now, the cells, some cells are 24 volt, others are different voltages. Depending on the voltages, I'm just using a 24 volt. So if I need, if you have 10 of them, 10 times 4, 24, they'll give you 240. 20 of them, 480. So can anybody, to get 600, can you guys divide 600 by 24 and tell me how many modules roughly I need? 600 volt by 24. 16 modules? 25? 25. So you need 20, all typically 25 modules. Now again, we're just for the sake of a calculation. Can I have thumbs up, Chad? We fully understand how it goes? Cool. Now, if these modules can give you, and again, just for the ease of installation, 10 amps. So, can you guys see it? I have 10 amps coming out of these modules. Now, how much power can I get? How much power can I get if I have 10 amps coming out of this? By the way, this is called the string. Can you guys see that this is called the string? All these three together, they're called them a string. Okay, anybody can tell me the power that's coming out of this system? I have 10 amps multiplied by what? 4, 48. What do you get here? 480 watt. This is how much current, how much power you can get out of this 3 panels, modules, at 480 if they're generating 10 amps. Can I have thumbs up, Chad? This is basic math, guys. We did it with Mr. Ryman, series circuit. Now, what happened if I need more power? What happened if I need more power? Well, guess what? You have another string. So I have, look at this. I have 10 amps here. I have 10 amps here. And I have 10 amps here. How many amps do I have here? Thank you, 30 amps. How much power? 30 amps times what's the voltage? What's the voltage of each string? 48. Anybody can do the math for me here? How much?
48. Shouldn't it be 72 per string?
Each string is giving you 10 amps. Here you go. So let's go 10 amps times what's the voltage? Times 3, because I have 3 strings, times what's the voltage for each string? 48 volt. Okay? I have 10 amps. Why? No, every string, the others are in parallel. One string is 48 and another string is 48. We put them in parallel. Okay, anybody can do the math for me, please? 48 times 10 times 3. Quick. How much? 1440 watt. Right? Anybody second? Any second? Yes, no? What? No, they don't. You don't put them in parallel. The 24 guys. Here's how we do. Let me show you. When you can't. What you said you can't. You can't put them in parallel if you want to. But in this case, the way we're doing them here, you're absolutely right. You can't put them in parallel. But in the way the string, all the modules in the string are all in series. Then to get more amps, what do? You put the strings in parallel. So these are actually tied together like this. Let me show you how it will be tied together. Here's string 1, and the second one here is string 2, and the third one here is string 3, and they're coming out. That's what these are.
I think he means
I mean your actual
each
string.
cell is 24 and you got 3 of them. 24 times 2 is 48. 24 times 3 is 72.
Oh, somebody gave me that one wrong.
Well, you asked for 2 cells.
I'm sorry. Okay, 70, thank you. You're up to 72. I got you. 72. So somebody do the math here quick.
So explain.
Thank you, Karen. I was really confused.
72. Okay, this will be 720. Thank you. Thank you. I see you. I see you. Okay. 72 times 10, is this right then?
Yeah.
Did we know that we need to multiply this one again by what? By 72. I see your point. 72, so I have 10 times 72 times 3, right? What's the math?
2160.
Thank you, sir. 2160. 2160. Sorry, Kerry. I don't understand what you're doing. Okay, you're absolutely right. Yeah, 24 plus 24 plus 24 obviously is 72. Once you guys brought that to my attention at the beginning, we did the whole math here. So, okay, so but does it make sense when you series them now? How much power you can get out of this system? Okay, so that's basically the system, how much power you can get out of this system. Any questions, any comments? Any question, guys? So the way they do them, they have diodes. Anybody knows why they have the diodes here? They have the diodes because they don't want you to feed back one string feedback into another. If there's a short circuit, one string will feed back into the other one. So they have diodes. Everybody knows what the diodes do. The diodes allow the current to go in one direction, not the other direction. And anybody knows why we have a fuse here? If there's a short circuit or a ground fault in the system, short circuit, between a positive and a negative, what do you need the fuse to do? Open it before we burn the equipment. Okay, then we combine them here, and we take them also into another disconnect here, and then you put your inverter, and out of the inverter you have another disconnect, and then you land them into a panel. You land them into a panel. So that's basically how the system is put together. Can I have thumbs up, Chad? We know how to do that? Would you guys be able to design a system? We don't have time next week, but if we have time, it's easy to throw a system like this. Any comments, any questions about this? I can't emphasize. You have the modules in series to get you the voltage. Then when you stabilize the voltage, then you put them in parallel. You put the strings in parallel to get you the amps, so you can get more power. Every string has to have a fuse to protect that string, right? Because of a short circuit, positive to negative. And then you have diodes because you don't want one of them to feed the other. If there's a short circuit in this string, you don't want the current to go from here all the way down to the other one. It can't go. The current only can go in one direction. Can you guys see that? The current always goes in one direction. Why do you think I have a disconnect here? Safety. Why do you think I have an inverter? So I have up to this point, I have 72 volts. Anybody can tell me what the output of the inverter will be? 241.20 volts. So I have an inverter that inverts the voltage from DC to AC. Can I have thumbs up, Chad? We understand it? That's basically the whole photovoltaic system. Why do I have two disconnects, guys, here? Disconnect and a disconnect. Safety, that's all. Safety. Nothing but safety. These are nothing but safety. Any comments, any questions about photovoltaic system? Any comments, any questions? Photovoltaic system. Now let me tell you a few sizing, and they will let you. Okay. Let me talk a little bit about sizing, guys. The way they size them, the same thing. Here's how we size them. Very easy, very simple. Now we know how they're put together. How do they size them? Joe, my friend, they take the wire here. Can you guys see that wire? That wire here, remember 24, 24, 24, that's the, back to my example. Here's my 24, my 24, my 24. This will give me all these together will give me what? 72, not 48. 72 volt. The wire that you do here, the way they size it, you take 1.25 multiplied by, this is how you size the wire. Are you guys with me? The amps of each one of these is 10 amps. Each one of these modules is giving 10 amps, 10 amps. Can you guys see that? I have 3 modules, not 2, 3 modules. Each one of them is giving 10 amps. Cool? And we did the math on this. We said just this one, this particular one here, this string here is going to give me how much power? We said, guys, 72 times power-wise, just power. It gives me 72 times 10, which gives me 7201. Just one string. Can I have thumbs up? Just one string. Cool. Let's go to how much current, how do you size the conductor? This is conductor. The conductors, here's how we size it. We take 1.25 times, what's the amp of each one of these modules? 10. But there's another 1.25 multiplied by 1.25 again times, what's the amp of the modules? 10 amps. Anybody can do the math for me? So you see how they size the conductor? I'll tell you why twice. Twice 1.25.
Why?
How much?
Why?
Yeah, can you give me the answer first? 1.25 times 1.25. Okay, so they multiply 1.25. This is weird because we always multiply how many times? 1.25. What's the answer? 15.6 amps. Cool. Now here's the question. The first 1.25, because of continuous load, right? It's continuously generating. Thumbs up, Chad. We understand. The black 1.25, because they want the modules. If you are to grab the hot and the neutral, the positive and the negative, and tie them together, that's called short circuit. Short circuit. They want the cables to handle the short circuit that's coming out of the modules. So basically, if you go to one of the modules right now and grab the positive and the negative of one panel and tie them together with a wire knot, you shorted them. That wire will be able to handle the short circuit current. Can I have thumbs up, Chad? We understand why the second one? One because of continuous load, the second one because of handling the short circuit. Okay, 15.5 amps. So based on this one, guys, then you need what? We need number, in this case, 15.6. You need 2 conductors, number 20, right? Because 15 is good to 15 amps. Number 20, not number 20, 15 conductors, number 12, number 12, and special type, A, W, G. These are special type cables that they use. Can they have a thumbs up, Chad? We understand? That's how you size this conductor here. Now, sizing this conductor the same way. Can you guys see it sizing this conductor the same way? Can you guys see it? And by the way, the overconduction device, the fuse, sizing the fuse here, the same way, the same calculation. So what do you get for this one? That will be a 20 amp fuse in this case. Because 15.6, what's the next standard? 20 amp fuse. Sizing this conductor, how many current this conductor is going to have? Remember, there's 10, 3 10s. So that will be 10 and 30, right? Because they're 30 amps. So this conductor will be 1.25 times 1.25 times 30. Can somebody give me the math, please, on that? Why 30? Everybody knows 30? There, do you see that each one of them is having 10 amps? What's the amp? What's the amps?
46.87.
Thank you. 46.8, 7.9 amps. Okay, now going to 310.15 B16, that will get you number 8. 310.15 B16, that will get you number 8, right? So from here, that will get you how many conductors? 2 conductors, number 8, A, W, G. And these conductors have to be rated for what location, right? Because they're outside. So these conductors could be T, H, they're DC. They have to be a special, they have to be special, up at this point, they have to be DC rated conductors because they're carrying conductors. THW, I believe that you can use a THW. 2 conductors. Why 2 conductors? Positive and negative. Positive, that's it. You guys just discovered how to size the whole system. The last thing I'm going to do, guys, is when you bring these down, can you guys see when you bring them down, you bring them in a disconnect. So I have, can you guys see it? I have a 20 amp fuse. What do you think the disconnect here will be? What's the next standard after 20? This is 30 amp disconnect. Okay, inverter. So I need an inverter. The only thing you need an inverter, how much power you need to invert? How much power you need to invert based on my example? 720 times how many? Times 3. What was that? 20. We did this math before.
2160.
2160. So you need an inverter that invert 240 volts slash 120, and I need it.
2160.
Thank you. 2160 watt. So when you go to buy this inverter, you need to tell them I need an inverter that can take me back to 24, 120, and handle at least 2160. Can I have thumbs up, Chad? We understand? Perfect. Now on the AC side, guys, when you invert it, now the inverter, you need to find the inverter current. On the AC side, you need to find the inverter current, right? Now, what's the inverter current? Suppose the inverter current was 20 amps. It has a 20 amps inverter. So what do? You take 1.25 multiplied by 20. Anybody can give me the answer, please? 1.25 times 20? 25. Thank you. 25 amps. And then these conductor will be sized. How many conductors? 2 conductors, number 10 AWG. These are the AC conductors. 2 conductors, number 10. Why do we multiply by 1.25 here? Because it's continuous load. It's continuous load. That's it. You guys have just sized an AC system. Anybody can tell me what the disconnect size here? I have a disconnect also. I need disconnect in this inverter here. If my amp is 25, what do you think the disconnect on the AC side is going to be? Next size up after 25 is what? 30 amps. 30 amps disconnect. You have just sized a system, a PV system. All what you need to do now, Aaron, my friend, get your conduits, pull your conduits, EMT conduits or PVC, pull these conductors that I told you about them, put a junction box. There will be a J box here. All this junk will be in a combiner. They call it combiner, and off we go. And from this side, where do you go from this side? You tie it to the panel. You tie it to your panel. Any questions, any comments, guys, about photovoltaic system? Photovoltaic system. So that's where you got your. Would you guys be able, if I give you an example, to size that? Maybe another example, Chad. So okay. Well, I'm not going to test you on that one this time. When we go to the commercial, guys, we're going to do the same thing. So if you know it in the commercial. Great, because the commercial is identical. The only, you know what in the commercial they do? The voltage becomes 28120 or 240. In our case, it's going to be 28120. That's all. Everything stays the same. Okay. All right, so let me take a snapshot of that one. Any question, guys, about this? Any question? So we talked about this picture. Great. So you're cool. Here's how it looks like when you put these on a building. Everybody have seen them. So all the panels that I was calculating for, guys, here's the 3. I assume this is the 3 modules, right? So here's your 24, 24, 24. That add up to 72 volts, right? Exactly. On the roof, combined together. And if you want to add the rest of them, you can get more voltages. Now remember the inverter that we were talking about. Everybody knows what the inverter does. It takes the DC into AC. You have to put it in a place where you have at least 3 feet, right? 3 feet clearances in front of it, like the clearances in front of the panels, because you need to work on it, so it needs clearances. You can have, for the commercial building that you guys are going to do for me, the A students only are going to do it. The B and the C are excused. So they're going to do a larger system. Instead of having 1 inverter there, what do? 2, 3, 4 inverters. That's all. Same system. Piece of cake. Piece of cake. Everything is piece of cake for you, Chad. So here's your inverter. You guys remember the inverter? I have my modules up here. Bam, bam, bam. Then come over here to a disconnect. From the disconnect, here's the inverter. From the inverter, what do? You tie it to the grid, and now you're feeding power to Excel. And your inverter, when you do that, your meter have to be a special meter that rotates in both directions, right? So so you have to have, if you are generating more than you're consuming, here's what happened. If you're generating more than you're consuming in your house, you start pushing energy into Excel so your neighbors can use your power. Now it's not as easy as this. There's an arrangement between you and the utilities. Excel has arrangement, guys. They don't allow you, because Excel does not want you to get into the business of making power and selling. What business are they in? Selling power. So there's arrangement where they can pay you a certain amount for a certain. So there's a lot of arrangement you have to do. So if you were to put a huge plant, well, guess what? They're not going to give you a whole lot of money out of it. So it doesn't make sense to sell them. It might be very cheap. That doesn't really make sense. So there's a lot of arrangement for selling back to the utilities.
That's how they get you on the rebate.
Yep. They get your rebate. They want to encourage people, guys, Excel and other utilities, they want to encourage people to have a smaller system that can offset probably 50% of their loads, 25 to 50% of your loads, okay, maybe up to your load. But after that, they don't want you to generate 10 times more than you consume and feed your neighbors. They don't want you to do that. Okay. Wiring methods that they use, guys, the same wiring methods that we use in 1 through 4 with some modification for the PV system. The PV cable, they have to be rated for PV cables that they use, the DC. Utilities, electrical utilities. Zach, my friend, electrical utilities will require you one requirement for the interactive system. They only require you one requirement. So your interactive photovoltaic system have to be rated, UL listed. If you lose the power, if you are to lose the power, your interactive system must shut down. Anybody knows why they want you to shut down if they use power? Because if you continue to feed, where do you think you're going to be feeding power to? To the grid, because the grid is down. And that could hurt somebody, right? So they want you, the only condition that they have is if they lost power, you have to shut down your inverter. So Zach, if somebody as a designer come to you and say, I want a backup power solar system, what do you tell them? Backup power, standby backup power. What do you tell them? The first thing you tell them, you can't do it unless they make it do, unless you have to have an interactive system with battery backup. You have to have a battery back. They make them. They make a battery backup. Interactive system has no batteries, guys. Interactive system with a battery backup, a battery is addition to it. You can add batteries. You can charge these batteries. If you lose the power, there's interactive that isolate you from the grid first, and then dump the power directly into a selected loads, selected group of loads. This is really interesting for those of you who are going to be interactive system work in parallel with the grid. It cannot work without the grid, the interactive system. You have to have the grid. It senses no power, shuts down. It's not a backup system. And there's an Article 705 interconnected electrical power production system. I'll talk about this one in the commercial project, guys. This requires you to do things. If you have two sources of power coming to the building, what do you need to do? You need to identify the disconnect for all these sources of power at the service. So that disconnect that comes into from a solar photovoltaic system right in here, my service is right in the other wall, right at the service. I have to see another source of power coming from the solar on a roof, and the disconnect is located in this wall, on this wall. So that's what anybody knows why? Because the firefighters walk in to shut down the power, not knowing that there's another source of power there. They need to be able to see that there's another source of power. Okay. Basically, this is the last thing I want to mention about these guys. Really, the system is not hard to design. We're looking for volunteers to install the system, guys. When if anybody would like to, in probably 6 months, maybe 5 months from now, we're going to be putting the system here. So if you want to come and do some apprentice work and do some termination, really cool. We have 10 panels. I think it's 2.5 kW system we're going to bring in here in our lab, and we're going to tie it directly to our lab. We're going to be doing it as instructors. So it's really cool. We bought the inverter, we bought the material disconnect. Everything that I showed you right now is bought. We're going to put them in the wall and energize that boy. Hopefully it works. Okay, there are two ways of connecting the photovoltaic system to your building. One way is the poor man's way. Let me start with the poor man's way. This is not the poor man's way. This is the poor man's way. So you bring your solar system, remember the whole solar system here, with the inverter and everything else, and you bring it in as a load, almost as a load, okay? The rich man system is right this one. See how they come? They come right into the line side of a disconnect. That's where you want to be. You want to be in the line side of a disconnect. What's the difference? Here's what the difference is. Let me show you here. Let me give you an example. If this is a 100 amp panel, then you are only limited to 20 amps system. If you do it this way, you must limit your load to 20 amps. Why? Because they tell you, do you see that bus rating here? This bus rating here? Let's say this bus was rated for 100 amp, and the overconduction device is 100. Look what they tell you if you do it this way. They want you to take that 20 amp, add it to the 100 amp. This is overcurrent protection device plus overcurrent protection device equal or less to the copper bars or the panel, which is 100 amp. This rule must apply if you do a solar photovoltaic system this way. Okay, can you guys see that bars here? That copper bar is 100. When you add the overconduction device here plus the main must equal or be less than 100. Okay? Can I have thumbs up, Chad? We understand? All right, let's double this system. How about if I have a 200 amp and this bus became a 200 amp? What's my maximum limit that I can generate? Anybody? I have 200. What do you think the maximum? Right here that I can bring in. Okay, let's do it. Here's a 200 here, amp. Here's a 200 here, plus. What's the number that I can add here? The largest number that I can add here to continue meeting this equation. The largest. Can I put 50? 50 plus 200 is what? More than this. So the largest number is what? 40. So this has to be 40.
How does that work?
40 plus 200.
It's 240.
You put 200 is less than or equal to 200.
So 200, if you add the bar.
The number that's on the right side of that should at least be 240.
We're missing one thing here. Hold a second. I think you're absolutely right.
Chad, I think you're trying to.
I'm sorry. No, I got you. No, it has to be less than. You're with me. I just forgot one little multiplier here, guys. 120%. I'm so sorry. 120%. My sincere apology. Now, does it make sense?
Yeah.
Okay. So now, does that make sense? That's what the requirement is. So when you add these two together, it has to be equal or less than 100 multiplied, the bus multiplied by 120%. So you can't add more than 20% on the bus, right? So if you do, is this right then?
Yeah.
So that would be 120 equal or less. At least one of us is awake. So yeah, there's 100, it has to be equal or less than 120% of the bus bars. And you can do your math. Any question, guys, about this? So that's a limitation of that one. I'm glad you caught it, Joe. I thought you were sleeping, man. So that one, if you put it here, there is no limitation. Can you guys see that? If you put it here, there is no limitation. You have to have a fuse, a disconnect, and a fuse here. No limitation, except from the utility. The only limitation that you have here, if you can, if this is size for 200 amps, theoretically, I can send 200 amps here. Can you guys see that? If your service is sized for 200 amp, I can theoretically, you have to coordinate with the utility, I can push 200 amps to Excel. Can I have thumbs up, Chad? We fully understand that. That's your photovoltaic system. Any comments, any questions? Everybody can see the difference between the rich man's way, the poor man's way here. You're only limited to 20% on the buses, right? So if your bus is 100 amp, I can add only 20% on 100, they'll give me 20. If it's 200, 20% on it, they'll give you 40. if you are doing it this way, which is coming from the line side of the meter, this meter will be dual direction. So it goes this way, right? It measures both ways. Then you need, then you limit, the only limitation is the cable, right? The cable that's going to go all the way, and Excel or the utility regulations. Any comments, any questions? So only for the A students, we're going to be designing this system, guys, for the commercial building next semester, I guess, or this semester, next part of the semester. Any comments, guys, about this? Any questions? So that's basically it. The most important things. Now to summarize, if you want to get more voltages, what do you do to the panels? You have multiple panels. You put them to get more voltages, you put them in series. To get more current, you put the strings in parallel, right? And we know how to size them. We size the disconnect switches and everything else based on 1.25 times the full load current of the string plus another 1.25. If you guys add this one to your reservoir of knowledge, you will be a much better designers. Some of you might be drafter for the rest of your life and you don't have to worry about this one. Just do it for chat. You know, it's really, it depends what you're going to be doing. Cool? Okay, that's all what I have for you.
The teacher had an article last year, I think it was.
Okay.
Magazine, about how to install your own.
Okay.